Awesome. Okay. Sweet. Hello, everybody. Thank you so much for joining us for Mad Scientists again. I'm so glad you're here. As always, if you're a student watching live, please type your name and school that you're from in the chat so I know who's showing up. Tootie, I'm so glad you were able to make it. Excited to have you here as always. Today is all about liquid nitrogen, which is one of my favorite experiments to do, just because there's so many cool things to do with it. So, first of all, we're going to talk about just how to make ice, right? Seems pretty easy, pretty straightforward, something you've probably done before. But what we're going to be doing is we're going to be making ice very quickly. So this is our home experiment so that you can follow along with this. You'll need a water bottle, clear water bottle that's been emptied out. You'll need ice cubes. You'll need salt, just regular table salt. And then distilled water. The reason we want distilled water is because we don't want anything else going on in our we don't want any impurities in our water that are going to make it freeze improperly. So what we're going to be doing is we're just going to take this ice, we're going to add a little bit of water, and then in our clear water bottle, we're going to fill this up, I'd say mostly full, with distilled water or purified water. You want to be careful with how it's purified. If it just says like purified drinking water, that doesn't always mean all the stuff is removed. So your best bet for getting this to work is to use distilled water, which guarantees there are no impurities. So close that, make sure it has a good seal on it. And then what we want to do is we want to sprinkle a good amount of salt into our ice cubes and water. So the reason we do this is because salt lowers the temperature of lowers the temperature of water, it lowers the freezing point of water. So now this water is going to be cold, colder than regular water because it won't be able to freeze at 32 degrees like it normally does. It's going to be much colder than that. And unfortunately, I thought I had more ice cubes than I did. So hopefully this works out, but you want as much ice as you can get in here. And this is just we're going to set this off to the side and let it get cold for a while. Again, you would want something that you could fill mostly around with ice. I couldn't find a perfect container for that today. You know what I could do? I'm going to do it like this because you can see there, now we have mostly covered the water bottle. So we're going to let that get really cold. I don't have my thermometer anymore. Unfortunately, that's still at the school and I haven't gone and grabbed it. But this is going to get below 32 degrees Fahrenheit. Hi, Dallas. I'm so glad you're able to make it. So we're going to set this off to the side. Again, you can do this at home. This can take anywhere from 15 to 30 minutes, depending on how much ice and the conditions that it's in. So we're going to set this off to the side and check on it every now and then. What we're going to really be looking for is for it to almost be frozen. And then if we get it right on the verge of freezing, what we can do is we can kind of shake it up and we'll watch the whole thing turn to ice right in front of our eyes. It's super cool. So while that happens, we'll move on to the liquid nitrogen experiment. So again, thank you so much for joining us. If you are from a middle school, please write your name and the school that you're from just for attendance purposes. And then we'll get right into this. So, liquid nitrogen. Definitely, if you're watching, ask as many questions as you can. I have the chat pulled up so I can read them as we do this. And if you need anything clarified or have questions or just want to know more about something, please ask. So, liquid nitrogen. is extremely cold. Um, its temperature is around negative 200 degrees Fahrenheit, which is way colder than the coldest temperature ever recorded on Earth. From weather, that is. So what we're going to be doing is we're going to be, I'm going to use the other bowl. We're going to be looking at all kinds of different things to do with liquid nitrogen. Because it's so cold, we can really do some interesting things. So we're just going to start off, and you can see there's already I haven't poured any liquid out. You can see there's that vapor coming out of this is called a dewar, named after the scientist who invented it. It's basically like a giant thermos, like a soup thermos. So you can see there's this layer right on top here of this vapor. This is all just nitrogen. If you hear the crackling, that's the crackling of the of the water that we just had in here from our last experiment, getting really, really cold and freezing almost instantly. Woo! So it'll be kind of hard to see into here through this camera, but there's ice crystals all around this bowl now, and it's just that ice or that water freezing immediately. So what we're going to do today is we're going to talk about what happens when things get really, really cold. So one example of this is a ping pong ball, right? Regular ping pong ball. If we throw it against the table, it kind of bounces. But if we put it in liquid nitrogen, what do you think is going to happen? And if you have a guess, feel free to share. We'll be doing all kinds of stuff, and I'll ask you what do you think is going to happen. So I have these tongs, so I can get things really deep down in there, and make sure they're getting completely covered in this liquid nitrogen and frozen all the way. So now, if I take one of these, yeah, that's right. So if I bounce this on the table, just dropping it, it doesn't bounce quite as well. Maybe about the same. But if I throw it against the table, oh, not cold enough yet. They gotta get even colder. And actually, while we're doing this, we'll get some other stuff going too. So this is a racquetball. So this is a very bouncy ball used to play racquetball. And it does not take a lot. And this bounces pretty well. If I just drop it from my shoulder height, right, it goes about halfway back up. So we'll get that. It's pretty bouncy. It's very elastic. And we'll let these things get colder and colder. So again, liquid nitrogen, extremely cold. So then, I feel like a chef almost, but instead of food, it's like tennis balls and racquetballs and ping pong balls. Okay. See how it sounds different, definitely. And just let that keep going. These are kind of old ping pong balls too. I have some newer ones that might work a little bit better. Oh, my camera got tilted up. There we go. So again, definitely ask questions if you have any questions. We're just going to keep on going, testing all kinds of different stuff. And let's see, our salt ice mixture definitely has some more time to kind of cool down until it's ready. Oh, the racquetball is getting close. So the way I can tell it's getting close is by the amount that it's bubbling when it's in there. So when I put something fresh in there, it bubbles a whole bunch. But when something's been in there a while and it's no longer warm, it stops bubbling as much. They're just not one to crack. But yes, they will shatter a lot of the time, and we'll we'll let these guys keep going, keep going. I'm also in my house, which normally I do this on like a cement floor, not a plastic floor, or a plastic table, so that might be a factor here too. But what we can do, I have another racquetball. If I just take this hammer, right, we're losing some stuff off the side, but nothing really happens, right? Except maybe bouncing my camera. But now, if we take this other racquetball that's been frozen, let's see if I can throw it first. Definitely doesn't bounce. Remember, it barely bounces, and then if I take my, oh, I need to do this on the counter, I think. Man, it's taking a serious beater. It needs to be a little bit colder. But you can see, right, I'm able to whack that really, really hard, and nothing happens. It's still a solid ball. It didn't crack. It didn't do anything, but it's just completely solid. So we'll let that keep going while we move on, and these take a while, so we'll start on the next things as well. Another thing we can do is rubber bands. So we have these obviously very stretchy rubber bands. We're going to put a few of these in here and let those cool down as well. So when elastic gets cold, it loses its elasticity, which is the term for its stretchiness. So if I take a rubber band, right, I can stretch this all the way. I could get it all the way around this bowl. But once it's cold, it's no longer stretchy. So when I take this, they're like spaghetti noodles now. And we can shatter them. And they just break. Woo! That sent rubber band pieces all over my living room. So I'll do this under the close cam, so you guys can see that a little better. So they just break apart. And you know, these bouncy balls and stuff like that aren't the only thing that will work like this. Fruit, which contains a lot of water, will have the same properties. So if we put some fruit in here, and I'm going to need some more liquid nitrogen in this container to make this work, right? We'll put some fruit in here, and since that water freezes really, really well inside that fruit, you can see it really bubbling now. Woo, and you can hear it too. So that fruit is in there, and it's getting really, really cold. Now, one thing you might see is, you might see me touching this, which seems really scary, right? Because it's so cold. But there's this really cool effect called the Leidenfrost effect, named after the German scientist Leidenfrost, who discovered this. And basically, I am so much hotter than the liquid nitrogen in temperature that once I touch the liquid nitrogen, it instantly boils. And that's what we're seeing here, right? We see the heat of the lime is just boiling away this liquid nitrogen because it's so much hotter than the liquid nitrogen itself. So I'm able to touch the liquid nitrogen because it forms a layer of nitrogen gas around my hand. And because of that, the liquid actually never touches me, just the gas does. So if I move quickly enough, I actually don't get burned, and it would burn me if I held it too long. So I actually don't get burned by this at all, because I am so much warmer. Okay, we're gonna need more. It took up a lot for that fruit. That was some very warm fruit. But you can see this lime has completely cracked, right? I haven't touched it at all, but it's just cracked. So this one, I'm confident. gonna start to break apart. Ooh, that's cold. So, and as proof, that one has a lot of water, so we'll let that go back in. Oh, here's another example. This strawberry shattered. There we go. We got some shattered strawberry now, right? So it broke apart into a tiny little pieces. That's because it was so frozen solid. Here's a raspberry, right? Oh, that looks really good. So if I did that to a regular raspberry, and I can as this proof, where did my fruit cups go? Oh, right in front of me, right? If I do this, smush, like it just stuck to my hammer. But since it's frozen, it shattered into these tiny little pieces of raspberry instead. And this lime is getting more and more cracked. Yeah, see, that's why it didn't freeze all the way. But there's the inside of it. You can see it's still liquid on the inside. Ow, I burned myself. Hi, Tootie. So, and another proof that this really is, and I'm going to need to go grab my gloves for this one. I will be right back grabbing my gloves. So I use oven mitts because oven mitts absorb the coldness. So what we're going to do is this is a regular banana, and I'm going to hammer this nail into this piece of wood. Oh, I broke my banana. So you see, So you see, the banana is still perfectly fine. It got split in half, but I'm able to nail this nail with the banana. And you can see I can pick up the piece of wood now, just from. And again, this was all just done by the banana. That's how hard and tough it gets, because you can see, I'll bring this up a little closer to the big camera. There's no way I'm getting that out. Like, that is stuck in there. And that was all just from the banana. So now, we're almost at, so you can see in here, the grape split in half completely. Same for the blueberry. So they just shattered inside there on their own. And that's because the expansion of the water inside the fruit popped it open. Is it frozen? Oh, it's completely frozen. Frozen solid. Like frozen solid. Nothing I can do to get rid of that. So, let's see if our racquetballs, I don't know if our racquetball is going to bounce or not. Or get shattered, I mean. Yeah. I have some other experiments, so I'm not going to keep cooling the racquetball. But we can do. There we go. There goes the ping pong ball. And again, it's also completely frozen, shattered into a bunch of tiny little pieces. Okay, so now, how cold is liquid nitrogen? I'm going to look up the exact temperature, because I'm blanking on it right now, in Fahrenheit. But, let's see. In Fahrenheit is negative 346 degrees. Negative 210 Celsius. That's how I know it as. Okay, so we're going to be done with that bowl because it's full of a bunch of shattered fruit. And I'm going to set that off to the side. There's a little bit of liquid nitrogen in there, but not much. Okay, so now we're going to move on to the bigger bowl. And I would like you guys to guess how many balloons you think I can fit in here. I'll get another book to prop up the close-up cam so you can see into this a little bit better. So, you think we can fit 6 balloons? Okay, what if I told you, like, this is the average size of a balloon? How many balloons do you think we can fit in here? 26, 21? All right, let's find out. If I need to blow up more balloons, I will. I only blew up 10. So what's happening is those balloons get super cold, though the air inside them cools down. And when the balloons, or when the air inside them cools down, it shrinks. Just like most things get smaller when they shrink. Does anybody know one of the main exceptions to that rule? What gets bigger when it gets colder? It's something that you use almost every single day. And it's weird because almost nothing else on this planet acts like this, except this one thing. So I'm just going to keep adding. This is our 4th balloon right now. So yeah, any guesses on what gets bigger as it gets colder? It's a material, and like I said, you use it almost every day. I hope you use it every day. Water, exactly, right? Ice gets bigger as it freezes. And that's so weird to think about because almost everything else in nature, everything else in science gets smaller as it gets colder, but not water. And that's actually a really good thing for us because if that wasn't the case, ice wouldn't float. And if ice doesn't float, that means we don't have the polar ice caps. And if we don't have the polar ice caps reflecting all that sun back into the, out of our atmosphere, our planet is actually way warmer. And if our planet's way, way warmer, life doesn't start the way we know it. So if water didn't get bigger when it got colder, we potentially might not even be here. Which is crazy to think about. Or we might look a lot different. Okay, so we're at, let's see, that's 9 balloons. I'm just going to keep going, right? Okay, we're at 10 balloons right now. And that air contracts because it's getting colder. And as it gets colder and colder, its like I said, its volume gets smaller. But one really cool thing about elastic, like the balloons are made out of. So remember our rubber bands that we were shattering? They're still stretchy after they've been shattered, once they warm back up. So you can see we have a whole bunch of balloons in this tiny little bowl, right? So now, one at a time, I'm going to use my hands for these first couple. I'm going to take these out, and I want you to watch what happens to them. So what are you seeing? They're coming back, exactly. So once that water starts heating back up, or not water, sorry, that air inside these balloons heats back up to room temperature, they start to reinflate all on their own. And what's really cool is the balloons are the material that makes the outside of the balloon comes right back to its bouncy space. So they don't pop most of the time. Sometimes they'll get little cracks in it when they're getting smaller and smaller. But you can see, like, as we can speed up the process too. So here, I'll do this one more time, just with one balloon, and I'll do the process quickly by throwing it up into the air. So the air heats back up and re-expands. All right, here we go. So we got a nice flat balloon. And bam, we're back to an almost normal balloon. It still looks a little funky, but it's warming up. So it happens really quickly, right? It warms back up, and that's because the air is so much warmer than the liquid nitrogen. So we have a couple more things we can look at. One thing that I've actually never done, but I'm really excited to try, is, oh, this is a cool thing. I don't know if you can see that. Let's see. There's some white stuff floating around in here in some of these balloons. It's kind of hard to see, but it looks like frost kind of. And what that is that's the moisture from my breath when I blew up these balloons. It got trapped in here. And then when it got really cold, it froze the moisture in the air from my breath. So the thing that I've wanted to try but never have is shaving cream. So let's find out what happens when we put shaving cream in here. Never done this. I'm excited to see what happens. I've done whipped cream, which is similar. Oh, sweet. Okay. You know what? I'm going to go get a little strainer thing. Scoop. So if this brittle, it actually feels a lot like, and it's breaking apart, but if I warm it up in my hands a little bit, I'm sure it'll go back to that shaving cream consistency. That's really cool. So the whipped cream worked a little bit better. It held its form, but there you can see it's holding its form still there as well. I'm going to try to fish most of this out because the next thing I want to do involves food. And I'd rather not eat. In fact, this isn't. I'm going to dump that over there. Oh, you know what I can do with that one instead? So, if I take some liquid nitrogen into some water with soap, oh, it froze the bubbles crazy. I have to add a little bit more. There we go. It's just free. Oh my goodness. It's like, wow. It's like shooting out ice. There it goes. We'll add a little bit more just to see that would be cool. I've never done it in this container before. fact, it looked like... Okay, so here's what's happened. It has completely frozen all the way up here. In fact, I might have broken my container. But down here is still liquid because the liquid nitrogen hasn't gotten down this far. It's just frozen all the gas right in here. So I turn this upside down. It'll drip out a little bit, but it's frozen all of that. Ooh, yeah, that's kind of... Okay, so to make this a little cooler, I'm going to get a different container. And I'm going to get some warm water. And the reason I want warm water is because it's going to be even more reactive with the cold liquid nitrogen. Mix our soap in. All right, let's try this one more time. There we go. That did the trick. All kinds of bubbles, so just pour it out of it. So each of these bubbles is filled with nitrogen. So when I pop it, that gas comes out. And it's going to keep doing that until, ooh, that's a big one, until all that liquid nitrogen is gone. So another thing we can do, right? A teapot. How does a teapot work? Does anybody know? How do you think a teapot works? Why does it whistle? So, it's not because anything is hot. It's because it's forcing air through this tiny little whistle end at the very top. So when you're boiling water, you are making steam, and it forces that steam out of the top. Here, I want you to get a better close-up of this. So you can see that steam is shooting right up. And it's whistling just the same because it's doing the same thing as when water boils. That's cool. So it's that nitrogen becoming, liquid nitrogen becoming gaseous nitrogen, which expands a whole lot more than the liquid form. And it's creating that whistling sound. Okay. Clear off my workspace a little bit. Let's see how much we have. Some left. Okay. I have too many experiments and not enough liquid nitrogen. Okay, so the next thing that we're going to look at is Cheetos. Who doesn't love a good Cheeto? So if we freeze Cheetos, and I wish you were all here for this, because I'd love to have you eat some Cheetos with me, but unfortunately we can't. So, when these Cheetos get cold, they trap that nitrogen gas inside them. So now I'm going to grab these and come around to the closer side of you so you can see this a little bit better. But when I eat this, I blow on it to warm them up. Not fair. I know, right? I can blow that vapor out of my mouth. Because my mouth, again, is so much warmer than the liquid nitrogen, it produces a lot of those water vapors and nitrogen vapors as I eat it. So, the same thing can be done with graham crackers or marshmallows. They do the same kind of thing. But I just wanted to share that. I always This is always one of my favorites. Does anybody have any questions so far before we move on? As you continue to watch me eat Cheetos in front of you. Okay. So, another thing I wanted to test, again, let's check on the water. Not cold enough. I think I needed more ice cubes for our at-home experiment. But I'll put instructions on how to do that so you can do that at home. So, again, remember, nitrogen. Where did my, oh, that's right, I spilled that in the very beginning. So liquid nitrogen produces a lot of gas when it warms up. So, because of that, if we put some liquid nitrogen into a closed container, it produces that gas. I have to move fast for this to work. Woo! Ah! I spilled it. Well, that was a good one. So, the same can be done with bigger containers too. And now, this is where my landlord gets nervous, right? Because I'm going to be shooting off bigger and bigger things. This one's a little trickier because I have to move quick. Woo! A lot louder, right? So, I'm going to do one last one. And this one I actually have to get a protective thing. And by protective, I mean I'm going to not blow a hole in my roof. Oh, that's where they went. So it doesn't take much. We don't need a lot. And then, let's see, where'd my lid go? I just had it. Come on. Anybody see where I put that metal lid to this? Am I going crazy? Guys, I think I might be going crazy. I could have sworn I just took that lid off. Oh, here it is. I was going crazy. So you can see from the last time I did this, it kind of dented it. Oh, lost it. Okay. Hey, there we go. You know what? I'm going to put the close-up thing over here by my plants. And hopefully, you'll still see. Yeah, that's better. That won't show as much. That's why we use this. Because otherwise that would have been through my roof. So, right? The more volume that it has to build up, the bigger the pop is going to be. So we have to be really careful with that. Hopefully I didn't hurt anybody's ears with those big pops. Is there anything else you would like to see me redo? Because I have a little bit of extra liquid nitrogen. I mean, we can redo one of these experiments. Or I have one more thing we can test, but it's not as exciting as some of this other stuff. That was great. I'm glad you liked it. So, any favorites that you'd like to see again? If not, I can go into my next things. So this one is we're going to be looking at rubbing alcohol. So in the rubbing alcohol, it normally doesn't freeze, right? This is 70% rubbing alcohol. So I'm just going to put this in here, in this container. And then we're going to fill the area around it with liquid nitrogen. So we're not actually putting it inside the container that has liquid nitrogen, but we're just cooling down, or sorry, has the alcohol, rubbing alcohol. But we're just cooling it down all around it. Hopefully my glass container doesn't break. Oh, you can see. Yeah, there we go. Okay, so it's cooling down more and more. And one thing we'll start to notice, no, we're not there yet, is alcohol, even though it's normally doesn't freeze like in a freezer, will freeze in liquid nitrogen because liquid nitrogen is so much colder than our freezer. It's getting a little cloudy. We're getting there. You know what? Maybe I will put just a smidge inside. There we go. That's a cool. Oh wow! I wonder if you can see that shape, that flowery shape. Oh my goodness! Speaking of flowers, I almost forgot. Like one of our coolest things. Flowers. So you can see it's now, I'll just get rid of that. It's actually frozen all along here. So we've frozen, and not all of it, you can see there's still some liquid, but it has frozen the alcohol along the sides of the container. So if we pour this out, and it's a lot more viscous and runny now, but you can see there's like group or like kind of a layer of frozen alcohol in here, and it's kind of gummy. I can actually scoop it up. So there we go. You can see frozen rubbing alcohol, which is normally very hard to get, but since we're working with something this cold, we can do it. Okay, so we have a decent amount left. So again, I'll show you again. Okay. So again, I can pick this up. One thing that some scientists like to do. Actually, I'll do the flour. I'll do the flour thing first, and then I'll show. So regular flour, right? Oops, lost one. Regular flour. If I hit it against the table, nothing happens. But when we freeze it, and this will take a couple seconds. When we freeze it, it's going to do the same thing, right? It's going to get brittle, and then it's going to become more fragile. So then once it's out, we can shatter the flour. You can see there's little petal shards over there now. We can do a whole bunch of flours at the same time, just to get a better idea of how this is going to work. Again, we're cooling it down really, really cold. Negative 350 degrees Fahrenheit. The coldest recorded temperature, I believe, on Earth in Antarctica was negative 84 degrees or something like that. So way, way colder than any weather we've ever seen on Earth. All right, so now as a group, right, we're shattering a whole bunch of flours and making a big mess in my living room. Like I say, every week, if you're not making a mess, you're not really doing science. So, any questions before we move on? Or wrap up, I should say. So one last thing that some people who'd like to play with liquid nitrogen will do, they call it the magic shower or magic rain, and that's because if I throw this up onto my head, whoo, I'm cold, whoo, but I'm fine. because, and I'm completely dry too, because it evaporates right away. I might have thrown some flower petals around my room, but that's okay. Okay, well that's most of our show. I have a little bit of liquid nitrogen here. What I can do is I can show you how it skids across a counter. So follow me on the close-up cam. Let's see. I think we'll do back here. Hopefully this reconnects. Hello, can you hear me? Yes, you can hear me, but you cannot see the close-up cam. There we go. Okay, so when this goes across a counter, you saw my dish rack. There we go. Okay, I'll do this at you. You see it sliding around. You know what? I'm gonna do the big close-up cam. Oh, you're messed up too. Of course you are. That's what I get for unplugging something. Oh, is it really not gonna work? Oh well, I'll have to mess with that later. But what I can do is I can just do this for now. Just so you can see this a little bit better. And the sound you're hearing is it hitting my carpet and evaporating. So, my carpet. So this is actually used for, liquid nitrogen can be used to kill weeds without any pesticides because it'll freeze the roots automatically right away without damaging anything. So, let me get this back up. If anybody has any questions, I'd love to hear from them. Thank you so much for joining us. And remember, if you are from a middle school, please leave your name and school if you haven't already done that. And thank you so much for joining us. I'm sorry my webcam isn't working. Okay, there we go. So, again, thank you very much, and I hope you have a great rest of your day. Again, feel free to leave questions. I'm so glad you're able to join us. We will be meeting here again next week, and I haven't decided what we're going to do yet. So if you have any ideas, pass them along to either the Google Classroom you're in or the YDC, that the Flagship coordinator that helps you out. And there's the last of our liquid nitrogen. So thank you, everybody, and have a great rest of your day. Bye.